So there's this map that could basically map out all we are in space and time. Now this line right here, this is space. I'm sorry that it's kind of off, but oh well. Space, and then here we are, this orange dot at Oxford Secondary School. One, say, here is everything in our future and past. This is time. So anything above the x-axis would be considered our future. Anything below is our past. Okay. So these equations here, they show how light travels through space. And basically it equals out to 299,792 kilometers a second. It's equal to 186,282 miles a second. Now because of this, there's a limit on our map. These lines we can all agree on because they're the speed of light. Nothing can go faster than light. That we know is a fact, therefore nothing can be in these two areas. So light is restricted to these two cones, therefore everything else slower than light must go within these light cones. If we wanted to send a message out to some guy on an asteroid somewhere in this region of space, in no man's land, that's an impossibility because that's outside the speed of light. I'll draw that on. Because we are going slower than the speed of light, we are condemned to in here within these green and blue dotted lines. To get to him, we would have to be going faster than the speed of light, which is the universal speed limit, therefore we cannot go past it, and that poor guy out in the middle of nowhere is going to be in the middle of nowhere forever without us. Now with this, we can map out anywhere in space and time that has reached and put myself into this position or you into your position of wherever. So we could throw myself in, let's say here, on my birthday, March 22nd, 1998. Yeah, I know, I look older than I am. And that would be my birthday. That's the day I was born. However, there's still the past before. There's the days of my mother and my father's birthday. So traveling back in time, you would have to be able to travel faster than the speed of light, up out of your future light cone, and circle around into your past light cone. It would mean going faster and faster and faster and faster, and finally escaping what light tells you you can and can't do, and then returning here. However, that is an impossibility, seeing as light is the fastest thing in the universe. That is the universal speed limit. We can't go faster, therefore that's out of the question. The only other way we could get into the past is by somehow turning our light cones so that our future light cone would then encompass part of the past light cone. Now, in our universe, we already see this happening in real life, in real circumstances. The only thing that can do this is called a black hole. Maxwell's waves equations, these two here, states that light and magnetic and electromagnetism have their own personalities, their own specifications as to how they move. Now I'm going to call Michael over, he is my assistant, to help demonstrate this in a really visual manner so that you guys can understand. Now, one of Einstein's experiments was to have two mirrors, like so, one that mirrors, and have light bouncing between the two, like this. And because the speed of light is a constant, this could be used as a near perfect clock. So I'm going to have my hands act as mirrors, and Michael, if you could turn the light on, thank you. Tap it back and down. Because it can act as a clock, each time it bounces, it can be used as a tick. So tick, 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 tick. Now, time and light would travel like that from a relative perspective. However, when things are moving, time changes for them and for us. So, Michael, if you could illuminate the light again. Now I'm going to have you do the ticking back and forth again, up and down, tick, tick, tick. Watch you walk back and forth. Tick, 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 tick. Okay? Thank you for that. As we saw with Michael, when his light bounced off the mirrors, it went in a diagonal, triangular fashion. Many mirrors, went in a triangular fashion, up and down. Now, you can say that yes, this is still the same time spent doing this tick. We have to conclude that because this tick, and this tick are all the same amount of time spent from our relative perspective, that for this light, it has to be traveling slower than what we see it to be traveling as. So it's going, yes, this is one tick, but then for it to go more distant, the same amount of time, it has to be traveling slower from its perspective. Faster from ours, but slower from its own perspective. Now, putting this into practice, if you were to send Michael off in a rocket at 99.94% the speed of light, out for 5 years, and then tell him to come back 5 of his own years. So buy his watch, go out for 5 years, turn around, come back for a total of, from his perspective, 10 years. Now for us, because of our own relative perspective, it would be more 29 years. So tying in what we were talking about with Michael and his relativity, moving back and forth with the light and it bouncing through the mirrors at the same time with the ticks, we can use another example of a black hole. You can see my lovely diagram of the event horizon. Sorry, Mo thought was passing by, and the singularity. So this is Michael traveling along, being pulled into the black hole. Each one of these X's are his light cones, which we talked about previously. So as you can see, each of his light cones, or his future light cones, point towards his future marks. Each X is in his future, which is in the next future, and each one previous is in the past, which is in the past of the last one, and the last one, so on and so on. For Michael, he's going tick, 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 into the singularity, or past the event horizon into singularity. However, from our perspective, we see tick, tick, tick. We continue going up further and further, taking longer times for us to see what's actually happening. Now that, again, for Michael, is traveling at the same speed as it should be. He's still going 1 tick a second. However, from our perspective, we're seeing 3 ticks in the first second, and then 1, 2, 3, 4, 5 ticks in the second, and so on and so on. It gets more and more elongated as he gets spaghettified into that lovely strand of atoms that are many miles long. As you can see with all of this lovely math and explanations, that the time travel is a possibility. However, it is very, very unlikely in our foreseeable future. Now, at some point, could some kid grow up and then get some crazy ideas from a video and see that and think, hey, you know what, I'm going to build something that can go as fast as light, go out and back, and that'll be great, I'll be a time traveler? Yes, that would be amazing. I would love to see that. But in my lifetime, I don't think that's a possibility, and well, I hope that it happens. Anyways, good night, people.